through inheritance create a new policy template argument for a class that accepts policies. The two primary ways of extending components. Closed. A component is closed if it's available for use by other components, but may not itself be changed. Perhaps we put it under configuration management. Perhaps, in your repository, somebody extracts a component, but they can't put it back in. They can change it all they want, but they can't put it in. They can't add it to the current working project baseline because they're not the owner. And it's not uncommon at certain stages in bigger projects where there will be a freeze. And the manager will say, no new additions, only bug fixes, here on out. Okay, so now I like to think of this in terms of application side and solution side, what I call application side and solution side software. Let me just describe it in words. We can look at the page a little later. Application side is that top level of a software project that focuses on requirements. They're responsible for meeting the requirements. The solution side is the layer below that does all the processing for those application side guys to use to get their jobs done. And it's a really good way of designing software. So the application guys don't do any of that nitty-gritty little, fussy little computing that's so easy to get wrong and have bugs in. They simply ask component, do this for me, I need this now, give me this. Okay. So application side focuses on requirements, and we don't expect them to be reusable. So they're focused on the requirements for this particular application. We can't reuse them on the next project. But the solution side, we really want those to be reusable. We want them to be usable on a whole bunch of different projects and in many different places on this project. And it's those solution side guys that we don't want to change. We really don't want to change. If lots of different people use them and I change it, I got lots of potential breakage. So, in big systems, the only thing that doesn't change is change. We always have change. Requirements, changing requirements, latent errors, performance issues, and you say, but requirements don't change, they're immutable. That was the old mantra, and it was a big fat lie. It was never true that requirements don't change. In the kinds of projects I worked on, we would get a bid package from a customer. And it would lay out the customer's requirements, and then we would write specs that interpreted those requirements in terms of our technology so that the customer could see, both for controlling our own product development and the customer could see what we were doing. And neither the customer nor we had perfect foresight. So the customer would one day say, oh, I forgot to tell you, I need this, I gotta have this. And you propose in your response to the bid package these set of requirements. Typically, you give the customer a requirements documents for review for the bid package. And it turns out later on, because you hadn't built it yet, ooh, that particular requirement is really difficult to implement the way we laid it out, really difficult. So what happens is, in any sane organization, the program manager and the customer go out and play golf. Okay? And on the golf course, the customer says, I really need this. It wasn't in the bid package, but I really need you to do the following thing. This product will not work for us unless it does this thing that it didn't get into our bid package. And the program manager will say, well, there's two ways we can handle that. One is that we can reevaluate our cost and we can submit a change request for cost and schedule. Or we have these three requirements that the way we stated them are very difficult for us to implement. But after analysis, we believe we can make these changes, which are easy for us to implement and serve your need just as well as the original statement. That is some negotiation, you know, and by the end of the day, handshake, done deal, okay? So no more cost for the customer, and you got out of that, you know, that insane statement you made that sounded perfectly plausible when you wrote it for the bid package because you hadn't written, you know, you hadn't developed the software yet, but now it turns out to be incredibly difficult to implement, just because of the way you laid out the requirements. So they change, they do. There's always change. You know, ideally, you don't want them to change. You don't want to see tsunamis of change, okay. But there's definitely changes. And latent errors, you know, anytime you write software, there's likely to be bugs in it and need to be fixed, performance issues. So how can we implement this open and closed principle in view of all these changes? Making changes can often result in cascades of changes to other dependent components. We'll talk about that more a little later on. So the open and closed principle says that components should never change, only be extended to meet changing requirements. And A, first statement, that doesn't apply to the application layer. Don't try to apply open and closed principle to the application layer. It ain't gonna. But keep the application layer simple calls into the stuff, into the solution side that does all the work. So having this mental model, that separation of application side and solution side, is a really good way to view projects. You know what to expect. So it's very difficult to build components that don't change but only support extension. Latent errors force change, performance issues force change. What we can do is represent the component by an abstract interface that provides a protocol that derived classes implement. So now we've separated the application side from the solution side through interfaces, and major parts of the solution side we've separated with interfaces. So with that interface, and by the way, we need an object factory too, for reasons we'll talk about in a few minutes. We can make all the changes we want, but those changes don't propagate. And the other idea is that once a component, you know, something that you want to be reusable, shouldn't be doctored for this particular application. Should not. When you first develop a reusable component, you know, it's not fully baked. It's going to change. You know, there's a period of time when, from the time we first write it until we're totally satisfied, yeah, this is the good stuff, well, it's going to have some change. But after that, after we say, yes, this is the good stuff, we do everything in our power not to change it. So what we want to do is extend it, not change it. So so we have these new requirements, you know, that involve that. What we want to do is build a wrapper that uses that reusable component and adds some of the new functionality to it. So our goal is to extend, not to change. So abstract interfaces are part of the recipe. Changes to derived classes which implement the interface do not break any client code because if they use the interface, and may not even require a recompilation of some clients. What we can't do is change the interface definition. Any change for that interface causes breakage all the way up. And you say, oh, that means you'll never change an interface. And I say, no, that isn't true. But for every time you change an interface, the code changes 1,000 times, probably 10,000 times for every time you change. So what you've taken is this enormous breakage problem and compressed it to this little tiny breakage problem. by using interfaces. It's only when your foresight in designing the language for the interface wasn't strong enough. The language wasn't rich enough. And even that, we're going to address today. I'm going to show you how to get around that problem today when we talk about the dependency inversion principle. So abstract interfaces directly support the open and closed principle. They must be extended, they're extended but closed to modification. They have no implementation, so they have no latent errors and they have no performance problems. So, you know, each of these guys, they talk with each other through interfaces. I have an example here, but instead of looking at this particular example, I want to look at another example. So this is a parser. We've used this for code analysis projects. This year we're not doing any code analysis projects. Probably next year we will do code analysis projects. But I tend to alternate back and forth between the federation tile stuff and the code analysis kind of stuff. But the model here is I've got a rule-based parser, and the way it works is a bottom-level guy that's a scanner. And what he does is he takes input from a file, say, and breaks it up into tokens, and then a semi-expression part that forms groups of tokens that are just the right size to do a grammatical analysis. And then the parser is just a traffic cop. He's handing out those rules he's handing out those semi-expressions to each rule in a rule collection. But notice that he's holding iRule pointers, interface pointers. Those pointers are actually bound to derived classes, but he's only using the interface language. That guarantees you will only use that interface language. So he only depends on the text of that interface. If I don't change the text of that interface, he's not affected. And what that means here is, as my application evolves, or I want to do a different kind of code analysis, or I want to extend the kind of code analysis, I just add or remove derived rules, and it doesn't affect the parser at all. No effect, zero effect. It's Liskov substitution, okay, at play, and because of Liskov substitution, that gives me extension. I'm extending the parser without changing it. And the same thing is true here. Each rule has a collection of actions. And the rule has a collection of pointers that are typed as this iAction interface. And so the rule just uses that action interface, and I can change the actions all I want, and I won't affect the rule at all. So it's a very, 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 very flexible design, extraordinarily flexible. Now, another part of that recipe is that I have a builder. So none of these guys, the parser doesn't have to know how all those parts come together. The parser isn't picking out all those parts and deciding which fit in. If that was true, when I added a new rule, I have to change the parser. But instead, I have a builder that's doing the assembly, and he's the owner of all the parts, and the parser just uses them. The builder creates derived rules, and he installs them in the parser. He says parser add, parser add, parser add. And for each rule, he creates some actions, and he says rule, take this action, add this action, add this action. So extraordinarily flexible design. And here, separating the scanner module from the parser module is an iToken collection interface, which buffers the parser from any change you want to make here. The XML document that you used in Project 1 is using a good part of this, only it is using an XML parts instead of semi-expression to parse the XML. So I didn't change anything in the parser. I didn't change a thing. All I did was I changed from semi-expression XML parts, okay, it's a kick. So extend, don't change. I didn't sit there and make changes to the semi-expression module to make it act on angle brackets, you know, on the less than and greater than symbols correctly. I substituted without change. Nothing changed. So reusable, 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 reusable. These parts are not, and that's fine. So we're using inheritance to extend that. For project 1, we have a NoSQL database, and it has a parser template argument. I'm sorry, payload template argument. So each application is going to have a separate payload. So all we have to do is change that template argument. We don't have to change the NoSQL database. I don't have to do any tinkering at all with that NoSQL database. I just change the payload. Open and close. So those are our two avenues, inheritance and templates, for making stuff reusable. Now, for a typical code analysis application, there's lots of stuff up here, display and the execs and stuff that are very application specific, and no way would we try to make them reusable. They're application specific. Okay. But all the stuff below, so this is application side, actually the builder is sort of halfway in between, application side, and this is the solution side. And we don't want that solution side stuff to change. All this is quite simple. This is where all the hard work is happening. And once it's done, once it's working, don't change it. Now, in project 1, yeah, let's say in project 2, so you have to, probably will need to implement marking visited for individual records, so that you can do this pulling out all the dependent parts, because dependency is a graph, and so when you traverse that dependency structure, you'll get into cycles. You can get into cycles, and if you don't mark visited, you'll sit there and spin forever until you blow the stack. So you say, okay, that's easy. I'll just put my metadata. Wrong. You just modified this reusable part to make it work for the repository. Right place to put it is in the payload. Absolutely the right place to put it. And you say, but that's more work. If it's more work, then maybe your payload design isn't quite right yet. Okay. So. Okay. So satisfying the open and closed principle, this just restates the principle. We divide it into application domain and solution domain, and in the application domain, we don't try to apply it. This is going to change for every single application, okay? But for the solution side, we try really hard on the solution side to apply the open and closed principle. So if we're successful in building these reusable components, each new project will need to build less on the reusable side and can focus on meeting project requirements. So when we're building 10 million lines of code, we don't want to build 10 million lines of code. We want to build 900,000 lines of code and reuse 9,100,000 lines of code. My arithmetic is right. Okay. right? That's what you want to do. And it says, that means that I got to be able to find what I need out of a lot of stuff. That says we need a repository that makes it easy for us to find stuff and allows us to control it. So anybody can extract, but you can't put it back in. It can't become part of the product baseline because you're not allowed to put it back in because you don't own it. So not only will work if reusable components can be extended, we almost always achieve extendability by providing for application design time binding. So what does that mean? Application design time binding. Two ways. Using inheritance, I can provide hook classes that provide virtual functions that the application defines. Remember, we talked about the command pattern. So there was up in the library, there was this invoker that knew about events, and it published this command. And applications derived from it to do whatever was appropriate for that application to satisfy the command. That's a hook class. A command interface was a hook class. The iRules and iActions are really hook classes. The parser provided iRule and iAction, and the application implemented those as derived rules and derived actions. And I factored all of the changing stuff into a package called rules and actions. So those don't appear. The interfaces iRule and iAction appear in the parser code, but the derived stuff does not. That's in a separate file, okay? So that users don't get tempted to go and tinker with the framework. The other way is to do it with template policies and traits. So NoSQL database. Repository needs payload for the repository. Some other application needs payload for that application. Open and close principle. Absolutely. So I'm going to skip this. So library designer supports extension by providing protocol classes, hook classes, template policy parameters and traits. Okay, so enough. So that's the open and close principle. The open and close principle was first stated by Bertrand Meyer. In the early to mid 90s, he was faculty, I think, at Berkeley, one of the California universities, and he stated the open and close principle, among several others. He was the inventor of the Eiffel programming language, which was the first serious implementation of design by contract, and he was a prime promoter of design by contract. The idea was that each interface had a contract, and the clients had to satisfy the contract, and the component had to satisfy the contract. And if there were violations in satisfaction of the contract, exceptions were thrown. And the idea of Eiffel was that now test is really built into the application through these contracts. Now, my own take is Eiffel isn't widely used because writing all those contracts, it's easy. So Bertrand Meyer gave as his examples a stat class. It's easy to write contracts for a stat class. But for a NoSQL database, might not be so easy to write contracts. Lots of stuff going on. Okay. But, and that's true of, any of the formal methods like that, it can be hard to apply them broadly to, large software bases. There are places where you really need them. if you're writing code that's going to control the flux density in a nuclear reactor, or the critical part of a flight navigation system, or a medical X-ray, the part that's controlling the dosage level and stuff like that, you might want to do that using formal methods. The thing you have to remember is that you can have bugs in formal descriptions just like you can have bugs in code. I think it's ideal if your language itself provides the formal definitions, and that's what Bertrand Meyer was trying to do. He was trying to build a language that developing code was an expression of a formal representation. But anyway, so now I want to turn to the next principle, which is the dependency inversion principle. So, have that guy up here, maybe I do. Dependency inversion principle. So the principle says high-level components should not depend on low-level components. Instead, both should depend on abstractions. Abstractions should not depend on details. Details should depend on the abstractions. Core idea. So as motivation, consider this very rational structure for a complex system. There's a top-level application side policy layer and a solution side implementation layer, and maybe a lower layer solution side of libraries we're going to use all the time. Okay. If we use concrete bindings, design time bindings, so this guy creates and uses instances of concrete classes, and this guy uses creates and uses instances of concrete classes here, a change in the utility layer could possibly propagate all the way up to the policy layer. Will that happen all the time? No. But maybe 10% of the time it would. If I make a change down here, maybe 10% of the time, I got to go and make changes all the way up here in the policy layer. That's ridiculous. Little tiny detail down, forced me to make a change up here. Crazy. Never make the software work. So what we do is instead we implement interfaces, abstract interface, and so the policy is using the text of this abstract interface. It's still, the pointer is still binding to the implementation, but it's only using the text of this interface. It's only allowed to use whatever declarations are here in this interface. So I can make all the changes I want here, and I won't break anything in the policy layer because all he depends on is the text of that interface. Except that he's got to call new and delete. And maybe to implement this interface, I needed 3 classes originally, and now I need 4. I got to add another class. So now I got to change this guy to create that 4th object. So what we do is we go to this structure. So now I have the policy layer talking, binding to the implementation layer with interface pointers, and the factory is responsible for creating whatever objects are needed here, and returns to the policy layer that interface pointer that the policy layer uses to use that interface. So interface and object factory. Now this guy is absolutely independent of any changes here. And this guy is absolutely independent of any changes here. Now, if I change the semantics, so it's compile time independent. If I change the semantics of what that interface means, I could cause a problem. But you don't want to do that. You go way, way, way out of your way not to change the meaning of that interface. So again, no breakage as long as I don't change the interface. If I change the text and interface, I break everything. But I will only change an interface once for every 1,000 times I change code. Maybe 10,000 times I change code. And I'm going to show you in a couple of minutes that even that, there's a way around that. Okay. So I've got an example here, but I've already shown you an example. The parser is an example of the dependency inversion principle. There are I rules, I actions. There was a builder that did all this. All this was in place in that parser. That parser is my favorite design. I've got lots of software I've written that I like a lot, but the parser is my favorite of them all. It stood the test of time. I designed this. A student, a doctoral advisee of mine, and I wanted to analyze. I've been interested in why big systems fail. And so the idea was, can we tell if a system's going to fail from its static structure? And my claim was, yes, we can. Well, there are lots of reasons a project fails. A project may fail because it has a horrible dependency structure. A project may also fail because everybody hates the program manager. Okay? Or the customer is totally unreasonable. Or we're totally unreasonable. Okay? Lots of reasons for project. But a major reason for project failure is static structure. We were able to demonstrate that in spades. And we did that. I designed the parser so that we could do static code analysis on, and we were examining a failed version of Mozilla. At the time, Mozilla was desperately trying to get they were Netscape, and they were trying to make the next version of Netscape so that Apple would use it as their primary browser. And Apple got tired of waiting for them and finally said, goodbye, guys. We're not waiting any longer. And they picked up Safari. And the Mozilla guys were heartbroken. They really were. When we downloaded their code to examine, I knew that this code base had failed. When we downloaded that code base from CVS, along came all their emails, and we were reading their emails, what was going on. What was happening was they would make a change, and there would be a fission of breakage. Because they had components, they're something called strong components. It means it's a dependency graph in which every node is dependent on every other one. Every package is dependent on every other, not always directly. A package A may depend on package B by depending on C, D, and E, and E depends on B, okay? But anyway, if they're in a group of mutually dependent files, and they had one as big as 65. 65 files were all mutually dependent. Through some very arcane path, but they were. Our analysis code showed that they were. What that meant was, if you change one, then it's your obligation to test every one of those other 65, because they all depend on you. You can break them. And in the course of testing it, you find these two others that broke, because I changed this one. And so now you got to change those. And each of those breaks free. And soon you have this fission of explosion. Boom! Of change. That happened. We could see from their email that was exactly, we can't change this because, well, it's so much breakage that we'll never fix it. That was what was happening. And, it was clear that that was their problem. Absolutely clear. Okay. From the stuff that we did. So, and that's, I wrote that parser to enable that kind of static analysis. So, I really, we've used that for several different pieces of research work. Several of my doctoral advisees have used it, and I've used it in class projects for years. So it stood the test of time. I'm really proud of it. So that's a good example. Okay, so now here's a classic structure, object factory interface structure. So here I have widgets, just a little demo. I have widgets, and so I have an iWidget interface, and the client wants to use any one of those. They have different, they all satisfy the iWidget interface, but they do things differently. Just like the parser uses the iRule interface, and there's a bunch of rules that implement that interface in different ways. And there is a widget factory that the client uses to get a pointer, a iWidget pointer that's bound to one of those objects. And if you look at the include structure, the iWidget.h doesn't include anybody, but almost everybody includes him. And iWidget factory doesn't include anybody, but lots of people include her. So client includes iWidget factory, and now the iWidget factory is included by the widgetfactory.cpp, and the widgetfactory.cpp, he needs to know about all these concrete components, because he's got to say new widget 1 or new widget 2, so he's got to have concrete. But the nice thing about it is that factories tend to be 100 lines of code, not 10,000. So it's easy to change, easy, quick to compile, and nobody else is affected. Okay? As long as I don't change this text, and I don't change the top level, I don't change widgetfactory.h, and I don't change iWidget, I can make all the changes here and all the changes here I want, no breakage. Don't affect the client anyway. And if I not only use the object factory and interfaces, but I build each of those components, each of the widgets, widget 1, widget 2, widget 3, as dynamic link libraries, then if I want to make a change, all I do is grab that one dynamic link library, go off to the side, make a change, test it, make sure it's right, copy it into the directory where the application is going to load it, and I don't build anybody. I don't rebuild anybody. Nobody. That's how Windows works. Windows is built on a component technology, COM, that uses interfaces and object factories. So when you do a Windows update, Microsoft doesn't send a technician to your house to rebuild Windows, right? They copy a DLL into the directory where Windows, when it starts up, loads it from. Indeed. Piece of cake. That's why Bill Gates has a nice, fat, thick wallet, because of the dependency inversion principle, and they knew how to use it. Okay, so let's actually look at the code. So the diagrams are nice, but let's take a look at the code and see how it actually works. Real simple little stuff. So this is in code widget factory, so I probably should have it right here at widget factory. So here's my widget factory. Okay, yeah, I already had a version running. I did. So so let's look at iWidget. So here's iWidget. So I have a. Can you see that all right? Is that big enough? Too big. So anyway, so in C++, C++ doesn't have an interface construct, but we use a struct because a struct is just a class, except that its access is public by default. A class's access is private by default. It's the only difference. They're absolutely the same. A struct can have constructors, destructors, all kinds of methods, whatever. But for an interface, we have a pure virtual function, do work. So this says I haven't implemented it. And I have a virtual destructor for reasons we talked about last time. Okay. And of course, do work stands in for all of the stuff that a typical interface might provide. And now let's look at widget factory.h. So here's widget factory.h, and so we just say this is a static function. So the factory, I index it with an integer to pick the widget I want. And then, and this could be let me come back to that. And the job of the factory is to return an interface pointer bound to that object. So the client can only use this interface language, but he's bound to a real concrete component. The reason I used an integer index here was that you can say, why don't you use an enumeration? Enumerations are nice. They're readable constants. They're named constants. It really helps to make code more understandable and maintainable, and that's true. But if I change it, that's a change in the interface contract, and I got to go recompile everybody. So on interfaces for object factories, you don't want to use enumerations. I have two choices. I can use an integer index, or I can provide a string, and have a map that took this string as a key, and each value was a creational function. Create widget 1, create widget, new widget 1, new widget 2, new widget 3. Okay, now let's look at the client, and then we'll come back and look at the parts. So here's the client. So the client says, iWidget star p widget equals widget factory. Because this is static, I don't yet have a widget to dot onto, so I got to have the static method. Widget factory : create widget 1. Now the factory might not have been able to create 1, and if it can't, I might have said 55. Client might. Okay, so this is going to return null pointer. If it can't create, it's going to return a null pointer. So I just test to see if it's, as long as it's not a null pointer, then I can do work. And then I must delete it, because you have to think of these factories as smart news. The factory can't possibly know when you're done with the object. And so it's up to you to delete it. Now, I actually didn't use that policy in my parser. The builder was around for the whole length of the project, and my model was, when I did it, which has been true, that all of those rules and actions were used throughout the entire project. And so now I had my factory owned them all, and it deleted them when it went out of scope, which is fine. But typically, a factory won't do that. A factory turns ownership. When you get this pointer, you become the owner of that pointer, and it's up to you to delete it. So I did. And then p-widget, create widget 2, do work with widget 2, create widget 3, do work with widget 3. I don't have a widget 4, but if I said create widget 4, back comes null pointer, and I say, whoops, I can't do it. So, and now let's look at the implementation of the factory, widget factory.cpp. Sure enough, here is switch on widget index, new widget 1, new widget 2, new widget 3, piece of cake. Easy. How can it be so easy? Piece of cake. Almost no code. And now each of the individual widgets are just implement the widget factory, and their CPP part is just trivial, because all I'm doing is, this is just a demo. So now when I run it, widget 1 working, widget 1 destroyed, widget 2 working, widget 2 destroyed, widget 3 working, widget 3 destroyed. Can't create widget 4, I'm done. That's an object factory. Piece of cake. Yeah. Now, so now So design, a lot of design is in surely thinking about the tasks and the major parts that your software, the major parts of the software and what tasks do they have to do. But a lot of it is language. How do I get that guy to do his thing in a way that's sensible and understandable? So, for example, in the query guy, or NoSQL database, my query guy, that is really nice language, query, dot select on these conditions, dot show, or from. You don't really understand. Nice language. But how about if your language, none of us have perfect foresight. Language just wasn't good enough. Later on, some changes happen. We need some new language. You say, oh my gosh, I got to rebuild all that stuff. I got to change the language and rebuild all that stuff. Well, maybe not. Maybe not. Suppose we do this. So here, forget for a minute interface 1 and interface 2. So now I have this product. This is like iWidget. And here's widget 1 and widget 2. Okay. And everything's working fine. And now my customer comes to me and says, Jim, I forgot to tell you, but I really need, and you say, oh, all those changes. Well, maybe not. So maybe I go away and I create an interface for that customer, that new stuff the customer wanted. And now I derive from both the original interface and the new interface. Okay. And now my factory returns me a pointer to this abstract product. But when to use the new stuff, I need a pointer to this interface. Can I do that? And the answer is yes. I'll show you how in just a minute. And now, 6 months later, your boss says, Jim, I know this is toward the end of the project. You've been working on this for a year and a half. But I needed to change. And you sit there and grit your teeth. But then, all right, we can do that. But not again. One time only. So here's the boss's interface. Okay. And we hear, now I have to change this, because I got to implement that new functionality. But the point is, I don't have to change any of this 10 million lines of code above me. So remember, this is solution side, and it's an application side. I got lots of code up there depending on me, and other parts of the solution side that depend on me. Okay. I don't have to rebuild them. I don't. The only thing I have to do is any parts. So of my 24 packages, if 2 of them need to use that new customer's functionality, I gotta recompile just those 2 packages. I add their use of the new customer's functionality to those 2 packages and recompile that. And if they're dynamic linked libraries, you just copy them into the library where this application loads them up. And the same thing for the boss's stuff. Works the same way. And you say, can this really work? And the answer is, oh, yes, it can. So here it comes. So let's look at abstract product 1. So here's the interface for the abstract product. Okay. So I had virtual destructor, as I should have. I had an identifier just for demo purposes. I have an operation A and an operation B, neither of which are implemented by the interface, of course, and the original component A and component B implemented both those functions in different ways because there were different components, and so they implemented, but they both satisfied that interface. And now I define the customer's interface, interface 1, with operation C, and I define the boss's interface with operation D. Okay. So normally we would put these in separate files. I think each interface should have its own file because not everybody's going to need all the interfaces. So you'd like to have just the components that are going to use the new customers, those two packages, just be able to include that one interface. Everybody includes the original interface, but for the customer's interface, just those two have to include it. So normally I would I make every interface in a separate package, but you know, this is a demo program, and so I wanted it to be easy to illustrate. So those are my interfaces, and here's my factory interface. So now I say abstract product star create product. Okay, so my factory is just going to give me an interface to the original, a pointer to the original interface. I could have done it separately. I could have had the factory provide pointers to the other interfaces, allow you to ask for that. I chose not to do that for a reason. We'll see how the design works in a minute. And here's how the client uses it. So the client starts out and he creates a factory and declares a pointer to that abstract product. That's the central, the original interface. And he says, you know, f.create product. And if that wasn't no pointer, then, you know, first product created is, and this is op A, does its thing, and this just announces what the product is. And then its size is, and op B just displays its size in bytes. Okay. And the other, you know, the other product, product 2, just says second product created, and the size is different. You know, but they both implement the interface. Now I have this uses interface. So let's see what's going on with uses interface. So here, I say, I'm coming in here with this product interface. And I say, interface pointer to interface 1, dynamic cast interface 1 from PAP. And you say, that can't work. And I say, oh, yes, it can, because let's look at how that's structured. So here, I'm trying to use interface 1. I got a pointer pointing to this guy, okay, that's bound here. And so now, my dynamic cast says, I'm casting it to interface 1 pointer. My dynamic cast says, do you implement this interface? The answer is yes, I do. Bingo, it works. And I get a pointer, it'll just let me access that. If I dynamically cast to interface 2, it doesn't implement interface 2, so it'll say, no, I can't give you that interface pointer. I don't implement interface 2. And vice versa for product B. So now, let's run it, and then we'll look at some of the parts. First product created as product A, its size is 24 bytes, product using interface 1. So here, I'm using the primary interface, and now I'm using the secondary interface. I'm using the customer's interface successfully. But I can't use the boss's interface. I didn't inherit from it. I didn't because I didn't need to, and so this would be a client error asking for that on the wrong product, okay? And now, second product created as product B, its size is, I'm using the primary interface, can't use interface 1, but I can use interface 2. Here I am using it. you know, probably I would have changed the factory to provide an index that would give me the primary, you know, I want to make sure I need to think about my factory interface so that if I want you to get these other pointers, I got to give you a way to do that. So I got to future proof by thinking about what the factory interface is going to be. Or I could, you know, you can work it this way, same deal. But the point is that now I don't have to have perfect foresight as far as my interfaces go. I can create a new one. Don't break anything. Don't break a thing. This is what Microsoft did with their component object model. Each COM object has a factory and an interface, and the interface derives from a higher level interface called iQuery, IUnknown. And IUnknown has a function query interface, and it just lets you say, I've got this interface, I want this other interface. And if it can give it to you, it does. That's why Bill Gates has a wallet that thick. That alone took him from millionaire status to billionaire status. Because that's what allowed them to build Windows, this complicated, you know, 70 million lines of code, Windows 10, something like 70 million lines of code. They never would have gotten that act together unless they had that technology. And then, you know, they've been using it for years. In fact, you know, most of the people are seeing what Microsoft did and making small improvements on it by using the core idea. This is the core idea. Cool. So we're future-proofed. You know how to do it. So let's, there isn't much more to look at. You know, if we look at the factory.cpp, what do? You know, return new product A, return new product B. And if we look at, we already looked at the client use interfaces where I cross-casted. Okay. So, and concrete products, you know, all they're doing is saying, here's my identity, here's my operation B, and, you know, so that's that. And this guy, you know, so A implements the original component A implements the original op A, the original op B, and the new customer op C. Okay, he was changed to implement that part of the component was changed, and product B implements op A, op B from the original interface, and now op D for the bosses. So piece of cake. Yeah. If you take design patterns in the fall, there is a pattern called the extension object. Okay. But it is. Okay. So let's see where we are here. There is a, if you go here to notes, there is an application side, solution side, little discussion of, you know, what we were talking about this morning. So if you need a refresh, it's right there in the notes and some conclusions about it. So the moral of all this is that when you build large complex systems, you want to divide them mentally into application side and solution side. The application side, you probably won't try to apply open and close principle. You probably won't try to apply dependency inversion principle because they're fairly simple. They're just saying, they're just saying, you know, do this, do that, do this other thing. And it's the solution side that are taking care of all those nitty-gritty details. That's the place where the bugs are going to happen. So there, we want interfaces and object factories. We want, and now we know how we don't have to have perfect foresight in designing our interface language. We can extend it. Interface language is really a really major part of design. Remember 2 or 3 weeks ago in Help Session Friday, I walked in and said, here's a language for querying. By the time I was done, you knew how to do it. I didn't talk about any, I had no implementation. I hadn't done the implementation. I knew it would work because I'd done similar things in the past. So what made that work? And you know, that wasn't the only way to do it. I'm not saying you had to do it exactly like that. You don't. But deciding what the language is a major part. So your design typically is, what task do I have to do? How should I break that up into parts so that each part has a single responsibility? And then how do I communicate between those parts? What's the language? Once those 3 steps are done, it's a piece of cake. Now it's just programming. Yeah, you'll go back and revisit the design, make little tweaks, you know, but basically it's done. So the moral of the story is incremental development, you know. Think first, tasks, parts, language, and then build a little, test a little, build a little, test a little, build a little, test a little. Keep it always running, build a little, test a little, always running. So when I implemented Project 1, I implemented DB Core, which was my prototype that I gave you. And then I implemented parsing. I'm sorry, I implemented querying. And then I implemented persist, because I was using a little bit of parsing with persist. And I had already implemented the XML document, okay, usable part. And so if you took the XML document and tweaked it a little bit to get it to work for your NoSQL database, you violated the open and close principle and the dependency inversion principle. Violated. If in Project 2, you take the NoSQL database that you designed in Project 1, and you tweak the metadata a little bit, violated the open and close principle. That's why the payload class is there, to represent what varies from application to application. All the rest should stay the same. You know, because, you know, this is the second NoSQL database I ever wrote, and it's your first. You know, you might decide to make some changes to the metadata without, you know, it wouldn't be too surprising. But after an iteration or two, and you say, now I'm really happy with this, never change it again. And you have the mechanism to do that. It's all there in the payload policy. Payload is a policy. All righty. So is there anything more I need to talk about? Let's see. We have about 8 minutes. Yeah, let me talk briefly about, so the principles, there's 4 of them. And I want to talk for a few minutes about the interface segregation principle. That's the 4th of the major ones. So if you look at the contents here in this presentation, open and close principle, list scope substitution principle, dependency inversion principle, interface segregation principle. These are the primary things. These are interesting, but of secondary importance. Let me translate that for you. These 4 will be on the midterm. None of these will. Yeah, secondary importance. They are. They're worth looking at, worth understanding, but you know they aren't central to the main focus here. So let's take a look at the interface segregation principle. So the interface segregation principle says, okay, you've got this nice string class. And I really like it, and along comes this application that needs a little bit more string manipulation. You say, okay, I can deal with that. Edit it. Along comes another application, you say, okay, I can deal with that. Edit it. Pretty soon, you've incremented your way to a big, fat, bloated interface. And by the way, if you change, you decide later on that that interface really needs to change a little bit. Not only are you affecting the people that use that interface, you're affecting everybody that uses a string. At a minimum, they got to be recompiled. Because I make any change to an interface, I change the code layout. It comes out on different boundaries now. So, the standard string class absolutely does not satisfy the interface segregation principle. Absolutely does not. What they did was, everybody that came along that wanted something, they dumped it in the string. That's why I like my string class better than theirs. First time I wrote a string class, I fell into that problem. I kept extending it. One day I looked at it and I said, oh, what a mess. Okay, stripped all that stuff out. And it's really easy to build little string adapters, really easy to build these little adapters, you know, without polluting that string interface. So what the interface segregation principle says is, clients should not be forced to depend on interfaces they do not use. So if you have all this stuff, so if I've added application 3's needs into my interface, application 1 and 2 don't need it. Application 5 and 6 won't need it. But if I make any changes, I got to at least recompile them all. At least. So the interface segregation principle says don't do that. It's much better designed to have the components support multiple interfaces, one appropriate for each client. And we've seen how to do that, 10 minutes ago, 5 minutes ago. So here's an example. Let me skip to the chase because we're short on time. The idea is this. I have a company that's building industrial doors. And they have 5 or 6 different products. One of their products happens to be a time door. Bank vault. Will lock at the end of the working day. Can't be opened again until 8 o'clock the next morning. And we have a remote control door. Door for a hangar at an airport. Trundle, 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 up that goes that huge door. If I combine both timers and remote controls into my door interface, if I make a change to timers, I got to go change the remote guys. But instead, I can provide an interface that describes the essence of what it means to be a door. And for timers, I mix in timer. And for remote, I mix in remotes. And now I can do all the changes to remotes I want, even change the interface. I don't break this guy at all. So that whole product line doesn't change. But if I combine them in one interface, I got to change all those other product lines that didn't use that remote control. I got to change them anyway. I got to at least recompile. And now it's harder for the developers, the maintainers, to figure out, which am I, what part am I using, where am I, what's going on? But here, I only have the maintainer for time doors only has this timer interface and the door interface, and he doesn't have to worry about all those other stuff. He doesn't have to know about them. Doesn't matter. And the same thing here. The remote control guys that have remotes and the door, doesn't matter. So multiple inheritance is really useful. You want to make them disjoint in C++. Now, you say, but also I can't do this with Java and C#. And yes, you can. because you can multiply inherit interfaces. It's just now a little messier. I got to have another part. So here, this would be an interface, and instead of inheriting the implementation, I inherit the interface, and then I got to compose with the implementation for that interface. Okay. So there's another part. Big deal? Nah, not such a big deal. You know, definitely can make it work. You know, there's some tooling on the Java side, things like dependency injection containers and stuff like that that help with this sort of thing. But that's the interface segregation principle. Really nice. Mix-ins are your friend. It's like going to a buffet. You know, you get your tray and you pick some of this and some of that and some of this other stuff, and whatever you want, that particular meal you got. Okay. Any of you ever go to Wegmans? Larry Boulevard? Wegmans has a buffet at lunch. Well, a buffet at lunch and dinner. A lot of people go and shop, and what they do is they go up, they pick a little bit of this, pick a little, have their lunch. What you do, if you ever do that, I do occasionally, because that's a good buffet. And you'll see a lot of the workmen, the contractors and stuff that are working all over that area, Fayetteville and DeWitt and all that stuff. They'll all come to Wegmans to have their lunch. But anyway, that has nothing to do with the lecture, so I don't know why I distracted myself. So, going back to the beginning, so open and close principle says that components should be open for extension but closed to modification. And it really means reusable solution side stuff. Don't try to apply it to the application domain. There probably would be places where you'd say, yeah, this really applies in this part of the application domain. But if I were a company, I was building a whole series of products, even my policy layer, probably a lot of that would be common from product to product to product. So I might there too. But usually you apply this to the solution side. Liskov substitution principle says any code that is declared to accept a reference or pointer to a base class must support a reference or pointer to a derived class without the client having any specialized knowledge of the derived class. Dependency inversion principle says that components should depend on abstractions, not on the details, and the details should also depend on the abstractions. So if I have an interface, the client binds to the interface, but also the component that implements the interface has to bind to the interface. So we've taken a client binding to a component and turned it into client binds to an interface, component binds to an interface, and the factory joins them. The factory is what binds that interface pointer to the specific derived object that's needed. Interface segregation principle says mix-ins make life simple. Mix-ins don't always work. There's lots of cases, I've been in design situations where my first reaction was to use a mix-in, but that mix-ins really need to be independent, not have shared functionality. You don't want to have common ambiguous declarations in the various parts that you're inheriting. Okay, so, but when it works really, really well. For product families, beautiful design, easy. So principles, you are now principled people. There are some more. I'll take one last minute, then I'll let you go. If you go up to the notes part, you'll find design principles. And so here I talk about single responsibility, encapsulation, least knowledge, value semantics, scope-based resource management, list-out substitution, open and close principle, dependency inversion principle, interface segregation principle. And all of these are fair game. You should know about these. You should be able to respond well to these. In two places, for the midterm and for your interviews. I post for you my prior midterms so that you can look at them before, while you're preparing for this year's midterms, you can go look at last year's midterms. I have, my solutions, the question posed, and my answer to it. But also, it's a great way to study for an interview if they're, if this is a job using C++, looking at those midterms, making sure you can answer all the questions. So don't look at the solution, look at the question. Can I answer that? Don't peek. Can I answer that? Okay. Good way to study for it. I've had a lot of students come back from an interview and say, that was good advice. They asked me several questions that came pretty much directly out of that. Same idea. Not because the interviewers are looking at my code. A couple of, a few of them do because they're my former students, but because we all, there's a common body of accepted practice that I use and they use, and I'm trying to represent that with these midterm questions. All righty, any questions before we break? There will be a help session tomorrow. We'll talk about Project 2. If any of you need to ask questions about how can I actually use your Project 1 in my Project 2, we can talk about that a little bit. I've addressed that some already in class, but we can go over it again if you want. But and then talk about requirements for Project 2 and then anything else that turns you on. In a sense, so the way I designed it, I had a selection that was two separate, although I think I segregated them into two. So the answer really is no, because I didn't separate them into two. We're certainly using it with the XML document.
I think this should under one of the assuming that this is not violated. We cannot reference derived class if this derived class is not correct for X of this function. Let me put I'm sure this is if there is a test function we cannot pass it.
Actually, there are ways to do that. There are something called the adaptive pattern ways to do that. But, so list-out substitution really is, there's two aspects of it. One is compile time. As long as you're supplying to that function pointers that are bound to a derived class that derives from the interface that the function has, then you're using list call substitution, period. But the other aspect of list call substitution is that you really shouldn't change, it's not stated in the principle, but you really shouldn't change the semantics of what that